All right, tonight I'll be doing the infinite line of charge. So we want to find E at this point P right here. When we have an infinite line of charge, that's in blue. Okay, P is a distance x away from the line of charge. And the density on this is uniform. Okay, uniform linear charge density. Okay. All right, uniform means constant. So what do? Again, we need to apply Gauss's law. Sorry, not Gauss's law, just Coulomb's law. So what we do is, well, we know that E is KQ over R squared, right? Say this is for a point charge. Obviously, the line is not a point charge, but what we can do is we can break up, this is an exaggeration, obviously, the line into infinitely many small charges, each we can consider as a point charge. And we call this here dq, and let's assume this is a y above the x-axis. And this dq produces a field at point P, okay, such that the field points away from dq. Draw a straight line here, like this. All right, this angle, we'll call it theta. If this is x, this is y, then this is r, the square root of x squared plus y squared. So now what is this electric field? Again, this is an infinitesimal electric field, dE equals K, the infinitesimal charge that produced it over the distance where it was produced squared, right? Now, since this is along the y-axis and we have linear charge density, then dq is lambda times the length, which is, again, infinitesimal dy. So this will be K lambda dy over r squared. So that's the electric field from one infinitesimal element charge, okay? And our job now is to get, if we want to get the total field, okay, obviously we have to integrate along the whole line right here. But you have to remember that E is a vector, right? This is the magnitude of it. This is the magnitude of the electric field. E is a vector, which means it has an X and a Y component, all right? So when we add vectors, forget about this one, you know, Newton's law or whatever, we break up the vectors into their X and Y components. We add up and subtract all the X's, get one X, add and subtract all the Y's, get one Y, and then reconstruct the final vector from that one X and one Y. Well, we have to do the same over here. We have to break this dE, this one, see the vector makes an angle theta with the x-axis. We have to break it up into X and Y component. Now, if we just look at this for a couple of minutes and think about the problem, we see that there's symmetry in the problem. In other words, if I go distance y below the x-axis, I will find another element dq, okay? This is also dq, capital Q, let's keep it consistent. Okay. Let me put it here. Such that the electric field at this points like this and equal in magnitude to this one, okay? They're both the same distance r from point P. Here's the dq, distance r from point P. They make the same angle with the x-axis. Obviously, you know, one is y below, one is y above the x-axis. So whenever we have these two configuration of vectors, So again, as I go in and add up all my contributions down the line, or then maybe from negative infinity to infinity, I'm going to encounter this element charge, and then I'm going to encounter this element charge. But when I do that, I encounter this, then I encounter that on my way up. I'm going to get two fields like this. And what's that going to give me? These two fields will have their y, whenever I add them up, their y components will cancel out, because this electric field has a y up and this electric field has a y down. Equal and opposite, they'll cancel out. And then we will double the x component. And then, of course, I'll find another element right here, equidistant from the origin with another element up here, such that the same thing happens where the y components for these two will cancel, and then the x components will add up. So as I go up or down the line, I will be eliminating y components as I consider segments equidistant from the origin or from the x-axis. So we don't need to worry about the y component. So we're saying, due to symmetry, only the x components survive. So now what I'll be doing is adding up all the contributions only for the x component. This is similar to finding all the x components of all the vectors, say in Newton's law, inclined motion, or whatever. And then all the forces, I get their x components and I add them all up. This is what I'm doing right now. The integral will basically do the addition for us. So now dE becomes dEx, becomes k lambda dy over r squared cosine theta, because the x component of dE is the cosine of that angle. So now my final electric field, this is the magnitude, and it's going to be pointing to the right, is going to be the integral. It's going to write the integral in general, k lambda dy over r squared cosine theta. Now my job is to, first of all, figure out the limits of integration. That depends on what my variable is. And then put everything here in one variable. I have cosine theta here, or obviously, as I move up and down this blue line, adding the contribution from each element dq, r is going to change, theta is going to change, y is going to change. So what x obviously remains constant. So now we have two options. We can put them all in, say, variable dy, so change all the variables to y, or change all the variables to theta. Okay, either way, things will work out. Okay, let's do the y integral. All right, so now if I look here at the triangle, cosine theta is x over r. So k lambda, I take them out because they're constant. Integral, here's dy. Cosine theta is x over r, and I have an r squared here. Okay. Also, x is a constant. Take it out in the next step. Now, I have my integral dy over r cubed, which is xk lambda integral of dy over the square root of x squared plus y squared, or just the cube, or just to the 3/2, x squared plus y squared to the 3/2. Okay. What are my limits of integration? Now my limits of integration is from minus infinity to infinity. I'm starting here, adding up all the contributions from negative infinity. Okay, and then I move up, 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 and I keep going up and add up everything to plus infinity. All right. So we look at this integral, it's in y, and it's an even function. So we multiply, go from 0 to infinity and multiply by 2 of dy over the square root of x squared plus y squared cubed. So here now we use some calculus. Now we can easily go to maybe Wolfram alpha and then plug this in, just this integral, and then it will give you an answer. Or we could do some u substitution. Okay. So sorry, this is x squared plus y squared. Yeah. So what if we take y to be x tangent some angle, doesn't really matter, alpha. Okay, x tangent alpha. Let me see, tangent alpha here, tangent to be y over x. Yeah, it will be theta. We can leave it as theta right there. Okay, and we plug them in here. Okay, remember x is a constant. So what is dy in this case? It will be x, derivative of tangent is secant squared d theta. I'm not changing any limits of integration just yet. I could do it if I needed to, but we can go back, put things in y, or keep them in the new variable. That's not what I want. I wanted, let me see here. Yeah, here we're going to theta right now. So now what do we have? So we have 2x k lambda. Let's not worry about the integrals, the limits. Dy is x secant squared theta d theta over, what do I have here? Square root of x squared, but y is x tangent theta, so y squared will be plus x squared tangent squared theta, and then here we'll have cube. Okay, let me get a final form, then I'll worry about the limits. So here 2x k lambda integral x secant squared theta d theta, denominator I factor out on x squared, and then I take the square root of it, it becomes an x, then I cube it, becomes an x cubed, right? X squared comes out as an x of the square root, and it gets cubed, times. Now I have the square root of 1 plus tangent squared. Well, what's 1 plus tangent squared? 1 plus tangent squared of theta is secant squared of theta. Okay. So again, I have a secant squared inside the square root, take it out, comes a secant, cube it, comes a secant cubed of theta. Okay. So what do I have here? X cancels with that. So I have x, 3 x's down here. So I'll have 2k lambda over x. Secant cube, secant squared leaves me with a secant in the denominator. And here's a, and then that's it. It's a 1 right there. Now what's the 1 over secant? Is the cosine. So now my answer, now my limits, I could go a change of variable of my limits, okay, from 0 to theta. I mean, from when y is 0, I can find what theta is. And when y is infinity, I can find what theta is, okay? Or I can integrate this, then go back to the y limits. Let's keep everything in y. What's the integral of the cosine? That's the sine of theta. Okay. Again, I want to get back to my limit 0 to infinity, but what's sine theta? Let's look at this angle. Sine theta is y over r. Okay. So sine theta would be y over r. So that will be 2k lambda over x, y over the square root of x squared plus y squared from 0 to infinity. Okay. So now when I plug in infinity in here, okay, and then minus the 0. So let's plug infinity in here. So I'll have 2k lambda over x. I'll have, when y is infinity, y squared plus x squared becomes more like y squared, right? And the square root of y squared is y, so I get a 1 over here. When I plug in a 0, I get a 0. So it's 2k lambda over x. And that is the answer. Okay. 2k lambda over x. And so basically E is EX is 2k lambda over x, x hat. There is the final electric field. All right, if over here we decided, since I already have an angle, right? I already integrated this and I got an angle. I can do a change of limit. So let's see how we're going to do this. So basically we can write E according to that formula is 2k lambda over x sine theta from 0 to infinity in the x and in the y, right? But those limits will not work for this. So basically I need to change these limits. So what happens when y is 0? And what happens when y is infinity? Let's look at the equation right here. X is constant, right? When y is 0, obviously x cannot be 0, so the tangent of theta has to be 0. So this implies tangent theta is 0. And the tangent is sine over cosine. This implies theta is 0. So we got the lower limit. Okay, so now E equals 2k lambda over x sine theta, and the lower limit is actually 0, just like the other one. But what happens when y is infinity? Let's go here again. If y is infinity, x is a fixed, it cannot be infinity. So the tangent theta has to be infinity. So this implies tangent theta equals infinity, or goes to infinity. It cannot equal infinity, but for the sake of the argument, let's say it is. So what makes a tangent infinite? Right? Theta is pi over 2, because the tangent is sine theta over cosine theta. When this is 0, then, when it's 90 degrees, the cosine is 0, tangent is infinite. So this would be pi over 2. And now I can go ahead and plug in pi over 2 for theta minus the 0. So 2k lambda over x sine pi over 2 minus sine 0. Sine pi of 2 is 1, sine 0 is 0. So I'll have 2k lambda over x. Again, if I was to write it in the vector, it would be in the x hat direction. Same thing. And this makes sense, right? When my y is 0, that means I am right here. The theta is 0. But when y is going all the way up to infinity, this angle approaches pi over 2, right? You're basically looking straight up again. This goes to infinity. Now this is, obviously it's going to be small compared to the length of the wire. When you look towards the edge of the wire, it basically looks like you're looking above. Okay? So both of these make sense. So this is using Coulomb's law. All right. The next video, I will do the same problem using Gauss's law. All right. Where we basically use the symmetry of the problem and Gauss's law to compute the electric field at the same point, P right there. All right. I hope this has been helpful. Thank you for taking the time to watch it, and I'll see you in the next video.